AIOPs prediction for server stability based on ARIMA model. Abstract: in today's competitive landscape, enterprises must constantly improve and speed up their IT operations to stay ahead. The application of AI and ML in IT operations will enhance the efficiency of IT operations while resolving IT issues quickly and reducing the alerts. The AIOPs is short for Artificial Intelligence for IT Operations, that refers to multi-layered technology platforms that automate and enhance IT operations through analytics and machine learning, ML. One important use of AIOPs is, it can provide predictive alerts that let IT teams address potential problems before they lead to serious issues or outages. One such use case in IT infrastructure is to predict the stability of the server. The stability of the server depends on various performance metrics like CPU, memory, disk, storage health, NIC, network health, and network services. IT teams can proactively work on the server when the server stability is predicted as low. To predict the stability of the server, the AIOPs involves data collection, modeling and prediction. In this paper, we propose an AIOPs-based framework for alert prediction for server stability. The framework includes data collection and pre-processing, time series modeling using ARIMA and alert prediction. We implemented data collection, pre-processing, time series modeling and evaluating and comparing the forecast of naive, average, and best-fitted ARIMA models. The event prediction is out of scope from this paper. For server stability, we have considered CPU utilization as a metric, and CPU utilization data is collected for the few data center servers. Introduction. Today's IT environment is highly dynamic, increasingly distributed, and heterogeneous, and that make an environment more complex. This complex IT environment poses challenges on IT operators for performing tedious IT operations, which encompasses all the activities involved in the setup, design, configuration, deployment, and maintenance of the IT infrastructure that supports business services. There are various products to monitor the IT infrastructure at the hardware, service, and application levels. These products for monitoring collect logs, metrics, events, and traces from distributed systems. The final goal of monitoring is to reach a level of technological development where we have tools that conduct root cause analysis with high accuracy and enable us to autonomously recover systems. To achieve this goal, we still need to shift from a data collection stage to insight and action-driven paradigm. There are many enterprise monitoring software in the market, which includes Micro Focus Operation Bridge, MFOps Bridge, Dynatrace, Datadog, AppDynamics, and Splunk Enterprise. The Micro Focus company offers a broad set of monitoring tools as part of its IT operations management, ITOM, portfolio. OpsBridge is an enterprise platform for ITOM and monitors entire infrastructure, gathering raw operations data and consolidating it with data from existing tools, e.g., network and virtual machine management platforms. OpsBridge centralizes data from various data sources, providing a single source of ITOM data. To show the health and performance of infrastructure and applications across IT environment, the hundreds of hourly and daily notifications and alarms are delivered by OpsBridge to IT operations teams. The following figure 1 shows the MF OpsBridge operation console with event browser, health status, service health, and performance dashboard. The event browser window displays an overview of the active events that exist in the IT environment that we are monitoring. The details include like date and time when the event occurred, the host system, node, where the event occurred, the application that caused the event, the severity of the event, the user responsible for solving the problem that caused the event, if assigned, etc. The OpsBridge Health Status window displays the health information of the OpsBridge deployment. To ensure efficient operations, OpsBridge keeps track of the health of its components and reports problems so that corrective or preventive action can be taken. Service Health window helps to recognize the impact of a problem on your organization's business services and applications. Different levels of measurement build on and combine based on predefined rules to present a broad picture of system health, rooted in fine-grained data. The Performance Dashboard window visualizes performance metrics in the form of a performance dashboard. Figure 1, Operations Bridge Operator Console with Event Browser, Health Status, Service Health, and Performance Dashboard windows in it. Source 1. The important features of OpsBridge with respect to reduction of events are topology-based and stream-based event correlation along with IOPS-based anomaly detection. By using these features effectively, certain extent event noise can be reduced. But still further, the event noise can be reduced if prediction framework which can efficiently and accurately predict future server utilization loads, peak loads, and their timing. Such prediction framework can be built using AIOPs methods. Predictive alerting is one of the abilities of AIOPs which use machine learning and analytics to identify abnormalities in operational data and predictively alert IT ops on these abnormalities that could potentially impact an application or service. The prediction framework activates the predictive alerting based on forecasted server utilization. The prediction framework can have a prediction window and that can be short-term, i.e., hours, or long-term, i.e., a week. If the server utilization is high in next prediction window, the predictive events can be raised so that operators can proactively react to the situation to ensure the server utilization is stable. To design and build the prediction framework, the first step includes data collection and pre-processing, and it involves fetching the unstructured data collected by OpsBridge for server utilization and then it is processed as time series and stored as big data. In the second step, AIOPs-based time series forecasting methods are applied to predict the future server utilization. In this paper our focus is on collecting and pre-processing of the data, transforming the data to time series, exploring the statistic characteristics of the time series and then performing the prediction of the time series using ARIMA methods. Final step is to perform the comparative evaluation of best fitted ARIMA model with naive and average models and deciding on which method best suits in prediction framework. 2. Methodology. The following figure 2 shows the high-level architecture of the predictive alerting IOPS pipeline process that includes components as 1. Data collection and pre-processing, 2. Time series modeling, 3. Predictive alerting. The following subsections describe these components and their working in detail. A. Data collection. The MF OpsBridge collects huge data from various data sources and stores it in a data lake. For system stability check, we are extracting only the CPU utilization metric data using the MF OpsBridge APIs. The extracted data is ingested into the NoSQL local DB for quick processing of the large volume of data. The MF OpsBridge collectors collect the data for CPU utilization every 5 minutes interval. In our predictive alerting framework, we have dynamic configurable window to decide on the data collection interval. In our study, we have set the interval as 15 minutes. The predictive alerting framework extracts the 3 sets of CPU utilization data for every 15 minutes. After data collection, in pre-processing step we perform the below steps and actions are taken accordingly on the data. Detecting N/A values. Detecting gaps and outlier analysis. Affected instances can be either removed, replaced with interpolated values, or preserved depending on application needs. B. ARIMA. In autoregressive models, forecasting of a variable of interest is done using the linear combination of the past values of the variable. If there is some correlation between the present value and the past values of the variable, then autoregressive models are good choice for the forecasting. The autoregressive model of order P can be written as the D refers to is the number of differences. The Q refers to the number of moving averages terms. C. Building the ARIMA model. To build an ARIMA model, the time series must be a stationary series. If the time series is not stationary, then differential process is carried out on series to make stationary. In testing stationary of time series, Dickey-Fuller test method is used to detect whether the time series is stationary or not. As a first step, we collect the server CPU utilization data for few selected servers in data center and mark them as original series after pre-processing them. Perform the pre-processing of original time series to ensure original series is smoothened. Calculate the ACF autocorrelation function coefficients and the PACF partial autocorrelation function coefficients. Estimate all tentative models orders, PD and Q using ACF and PACF values. For each tentative model, estimate model parameters using OLS method. Then compute the sigma square, adjective R square, AIC, SBIC, and number of significant coefficients. Choose the best model having lowest AIC, SBIC, and sigma square and highest adjective R square. 3 Results and discussions. A. Data analysis. The MF OpsBridge collects huge data from various data sources and stores it in a data lake. For our study, we extract only CPU utilization metric data for few data center servers. On these servers, the CPU utilization data gets generated for every 5-minute interval. The collected data spans for 2 months and it need pre-processing as it contains missing and inconsistent data. The processing step involve cleaning and exploratory data analysis, EDA. EDA is geared towards understanding the data exploratory visualizations, histograms, box plots, scatter plots etc., and correlation analysis which bring out the relationships and other patterns. The cleaning step in the processing can include 1. Detecting N/A values, 2. Detecting gaps and 3. Outlier analysis. Affected instances may either be removed, replaced with interpolated values or preserved depending on application needs. Before time series modeling, the below pre-processing steps carried out on the collected time series. I. Detection and treating missing values in time series. The time series models require that there be no gaps in data along the time index, and so simply omitting observations with missing values, and reindexing as if there were no gaps, is not an option, as it might be for non-time indexed data. Instead, the missing values need to be replaced with judiciously chosen values before fitting a model. Here, we used the interpolation technique to estimate the missed values. One of the simplest method used is linear interpolation, and that requires knowledge of 2 points and the constant rate of change between them. 2. Identifying outliers in time series. Outliers are extreme observations relative to the rest of the data. Outliers can corrupt model estimates and consequently result in less accurate predictions. Isolation Forest's approach is used to detect anomaly in the time series, and it identifies anomaly by isolating outliers in the data. The contamination parameter refers to the expected proportion of outliers in the data set. This value is set to 0.01. 3. Resampling of time series to hourly averaged. A common solution to handle the imbalanced time series is to resample the data. The resampling strategies change the distribution of learning data in order to balance the number of rare and normal cases, attempting to reduce the skewness of the data. So all the time series data were resampled to represent hourly averaged after fixing missing data and outliers. 4. Identify trend, seasonality, and correlation in time series. The most important EDA on time series data is to identify trend, seasonality, and correlation. To inspect each time series for the trend and seasonality, the time series is decomposed into the 3 components as trend, seasonality, and noise. To inspect correlation in time series, the ACF, autocorrelation function, and PACF, partial autocorrelation function, are used. We have set lags equals 50 to compute the ACF and PACF for all the time series. V. Evaluate stationarity of time series. To test the stationarity of the time series, we have used augmented Dickey-Fuller, ADF, test. The null hypothesis will be rejected if ADF statistic value is less than the value at 1%. So the time series is stationary, else it's a non-stationary. The figures from 4 to 9 provides the EDA results for CPU utilization time series corresponding to 6 servers in the data center. The table I provides the summary of time series analysis. Based on the output results from figures 4 to 9, the summary has been derived. We have divided the time series into 2 sets of data, train data and test data. We followed 95% train, 5% test ratio to split the time series. Train data is used to create a model and forecast, and test data is used to validate the forecast. B. Modeling. Once the time series trend and seasonality components are analyzed in the data analysis step, checking for the stationarity of the time series is very important, as ARIMA modeling is applied for stationary time series. When the series is not stationary, time series differencing or detrending is applied. For seasonal data, one may require seasonal differencing in addition to non-seasonal differencing. After time series differencing and ensuring the series stationarity, the optimal AR and MA terms are decided. Using the ACF and PACF plots, we get a range within which the parameters P, Q should lie. I. Modeling TS, Server 1 CPU Utilization. ARIMA performed the ADF test for checking the series stationarity, and it implied that the series is non-stationary as P equals 0.144. After one difference, the time series became stationary. ADF test result P equals 0.01. Using the auto.arima function with D equals 1, the optimal model was selected as ARIMA 2,1,2, with the lowest AICC of -1511.544. The residuals analysis is performed using fitted model residual data. The Ljing box test of the residuals demonstrated no autocorrelation in the residual. Performed the Shapiro-Wilk and Yark-Barrett test to check the normality distribution of residual. The tests fail to reject the null hypothesis. H0, data is normally distributed, indicating still certain portion of residual is not captured by the ARIMA model. SARIMA, there is not much seasonality component in the time series. The best fitted SARIMA model remains same as ARIMA, 2,1,2. 2. Modeling TS, Server 2 CPU Utilization. ARIMA performed the ADF test for checking the series stationarity, and it implied that the series is non-stationary as P equals 0.445. After one difference, the time series became stationary, Adf Test result p equals 0.01. Using the auto.arima function with d equals 1, the optimal model was selected as Erima, 2,1,3, with the lowest AICC of -456.957. The residuals analysis is performed using fitted model residual data. The Ljing box test of the residuals demonstrated no autocorrelation in the residual. The statistic of the test is 22.992274 and the p-value of the test is 0.28917444, which is greater than 0.05. Thus, we fail to reject the null hypothesis of the test and conclude that the residuals are independent. Performed the Shapiro-Wilk and Yark-Barrett test to check the normality distribution of residual. The tests fail to reject the null hypothesis. H0, data is normally distributed, indicating still certain portion of residual is not captured by the ARIMA model. ARIMA, there is no much seasonality component in the time series. The best fitted ARIMA model remains same as ARIMA, 2,1,3. 3. Modeling TS, Server 3 CPU Utilization. ARIMA performed the ADF test for checking the series stationarity and it implied that the series is stationary as p equals 0.043. Using the auto.arima function with d equals 0, the optimal model was selected as Erima, 1,0,2, with the lowest AICC of -457.512. The residuals analysis is performed using fitted model residual data. The Ljing box test of the residuals demonstrated no autocorrelation in the residual. Performed the Shapiro-Wilk and Yark-Barrett test to check the normality distribution of residual. The tests fail to reject the null hypothesis. H0, data is normally distributed, indicating still certain portion of residual is not captured by the ARIMA model. Inspected the ACF/PACF of the residual, and found the spikes at the seasonal periods like lag equals 24. ARIMA, the auto.arima function with d equals 0 and d equals 0 is performed and the optimal model was selected as ARIMA, 2, 0, 1, 1, 0, 1, 24 with the lowest AICC of -507.926. The Ljing box test of the residuals, whose p-value is 0.094022, demonstrated no autocorrelation in the residual. Performed the Shapiro-Wilk and Yark-Barrett test to check the normality distribution of residual. The tests fail to reject the null hypothesis but the residual distribution is around the mean, 0.002. 4. Modeling TS, Server 4 CPU Utilization. ARIMA performed the ADF test for checking the series stationarity and it implied that the series is stationary as p equals 0.01. Using the auto.arima function with d equals 0, the optimal model was selected as ARIMA, 2,0,2, with the lowest AICC of -457.512. The Ljing box test of the residuals, whose p-value is 0.601513, demonstrated no autocorrelation in the residual. Performed the Shapiro-Wilk and Yark-Barrett test to check the normality distribution of residual. The tests fail to reject the null hypothesis. H0, data is normally distributed, indicating still certain portion of residual is not captured by the ARIMA model. Inspected the ACF/PACF of the residual and square of the residual and found the spikes at lag equals 2 indicating there is an heteroscedasticity effect in the time series. ARIMA, there is no much seasonality component in the time series. The best fitted ARIMA model remains same as ARIMA, 2,0,2. C. Forecasting. All the evaluated and finalized models were used to forecast or predict the future values of CPU time series. The forecasted results used to evaluate the accuracy of models using below accuracy metrics. From Figure 8 to Figure 11 provides the forecasting plots of naive, average, ARIMA and ARIMA models applied on CPU utilization time series corresponding to 4 servers in the data center. Evaluation metrics. There are several performance metrics to measure the accuracy of the forecasting methods. Here are few important metrics we have considered to evaluate the performance of the 4 models. I. Mean absolute percentage error, MAPE. It is a measure of forecasting method prediction accuracy in percentage. Any forecast with the MAPE value equals 10% is observed as highly accurate. The value between 10% and 20% is considered good, while 21 to 50% is supposed to be reasonable. The value greater than 50% is considered inaccurate forecasting. V. Root mean square error, RMSE, is a standard derivation of the prediction error. Equals V1, dash. 2, equals 1. Forecasting results. the tables 2, 3, 4, and 5 provides the summary of forecasting results. In most cases, the seasonality behavior does not exist as the workload on these servers is very dynamic. So there needed of transformations of data to build a decent forecasting model. Only in case of server 3, the seasonality component exists and ARIMA model provide better predictions than ARIMA. The ARIMA model's MAPE value is 0.104 and which is less than ARIMA model. For conclusion and future work, we developed an ARIMA and ARIMA model to model the CPU utilization forecasting for the data center servers in IT environment by using Box-Jenkins time series approach. The historical CPU utilization data were used to develop several models and the adequate one was selected according to performance criteria like AIC, SBC, standard error, and maximum likelihood. The CPU usage is dynamic and these fluctuations in CPU usage of servers in data center affect the time series forecasting model's accuracy. In this study, the ARIMA having first two AR terms and first two MA terms are performing better without overfitting the data. The results obtained proves that these models can be used for modeling and forecasting the CPU utilization of servers in IT environment. These results will provide to IT operators in making proactive decisions. As future work, we will develop other models by using a combination of qualitative and quantitative techniques to generate reliable forecasts and increase the forecast accuracy. We will also try neural network approach to compare it with ARIMA's results to confirm the AND's strength. A. Naive model forecasting results. B. Average model forecasting results. C. ARIMA, 2,1,3, model forecasting results. Figure 9, Server 2 CPU utilization forecasting plots. A. Naive model forecasting results. B. Average model forecasting results. C. ARIMA, 2,0,2, model forecasting results. Figure 10, Server 3 CPU utilization forecasting plots. A. Naive model forecasting results. B. Average model forecasting results. C. ARIMA, 2,0,2, model forecasting results. Figure 11, Server 4 CPU utilization forecasting plots.